Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Lesson 8, Informally Fitting a Line. Okay, so what's our objective here this time? Well, our objective is to students will informally fit a straight line to data displayed in a scatter plot, and students will make predictions based on the graph of a line that has been fit to data. Okay, so we're going to do a best fit line and make predictions using that. So here's the first example. Example 1, housing costs. Let's look at some data from one Midwestern city that indicates the sizes and sale prices of various houses sold in this city. And the data source came from Trulia in Milwaukee, and that was accessed in the year 2013. So this is almost 5-year-old data. Okay, so they have the square footage of the houses and they have the cost of the houses. And it's really hard to see anything from just a table of values. So in math, what we will do is we'll create a scatter plot, okay, bivariate data. So we have two variables, size and price, and we're going to plot them. So down below is a scatter plot of the data given. They've done it for us. So across the bottom, they said size in square feet, and then the cost of the house, the price in dollars up the left side, where this is $40,000 per grid mark, because there's 5 of them to get us to 200,000. So there are some dots way down here. So houses that are around 1,000 square feet or less look like they're around right here is about $80,000. So if I look here, well, here's $59,900, 956 square feet. That is probably this dot right here. Okay, just under 60,000. Okay, and so that's how we're graphing these. We're taking the square footage, going over to the dollar amount, and that's what determines where the dot is located. Okay, so now with that said, there's some questions to be asked here. And first thing I look at when I look at scatter plots is, do I see a pattern? Could I draw a line of best fit somewhere through here? And it would probably look something like that. So all these dots are fairly close to this red line right here. So as the square footage increases, so does the price of the houses. Okay, so let's look at some questions on the next page. And exercises 1 through 6. Number 1 says, what can you tell about the price of large homes compared to the price of small homes from this table? Well, if I go back to the table, the big homes cost a lot of money. This 5,000 square foot house is over $1 million. And then 4,400 square foot house is $800,000, and so on. And then if I look at a smaller house, like 956 square feet, that was only $59,900, just under $60,000. So what I would say here is, the larger the house, the more it costs. Okay, the larger the house, the more it costs. Okay, number 2. Use the scatter plot to answer the following questions. A, does the scatter plot seem to support the statement that larger houses tend to cost more? And in this case, that's kind of what I said in number 1. So I would say yes, because it's a positive trend. Because as square footage increases, the prices increase. Okay. B says, what is the cost of the most expensive house and where is that point on the scatter plot? So if I go back here, the cost of the most expensive house is $1,050,000. So to answer this question, the cost is $1,050,000. And it says, and where is that point on the scatter plot? Well, it's at the point 1,050,000. Actually, that's my y. So it's something, comma, 1,050,000. So that's my y value. So if I go back, okay, price was y, and it is way up here, and if I go down here, it's over 5,000. Well, the value is right there, 5,232. So 5,232. So the point on the scatter plot is at 5,232, comma, this is my comma between x and y, not to be mistaken for a comma in our numbers, and the y value is 1,050,000. And that value is right here on the scatter plot. Okay? And number 2C says, some people might consider a given amount of money and then predict what size the house they could buy. Others might consider what size house they want and then predict how much it would cost. What would you use the scatter? How would you use the scatter plot in example 1? Okay. Well, I think that I personally would use choose a value that fits my budget. So I would choose a dollar amount and see how many square feet that would get me. We don't want to live above our means. Okay, so let's just say I think I can afford $500,000 for a house. So I would go to the graph here and I would go over to $500,000, which is about here, and I'd look for a house in this range. Well, unfortunately, there aren't any. This would go over my budget, so I would probably go to the next one down, so it's either this point or this house, depending on what their amenities are. Those are the same are not same price, but the same square footage, same price, different square footage. So I'd probably go with this house here at, looks like roughly 2,000, what, 400 square feet, something like that. Okay, so that's how I would do it. Would it be wrong to go the other way? No. If you wanted to know how many, if you wanted a 3,000 square foot house and wanted to see how much that would cost you, you could also do that. And that's what this says here. Estimate the cost of a 3,000 square foot house. So if I estimate the cost of a 3,000 square foot house, then I'll get rid of all this other stuff on here. And 3,000 square feet is right here. And so it's somewhere on this green line right here. Well, if I put that scatter plot, if I put that line of best fit back in right here, that's an approximation, of course, but right here is where it hits, and I'd come over here, and I'm probably looking at, I don't know, $520,000 roughly. So the estimate would be, I don't know, $520,000. That's my estimate. E, do you think a line would provide a reasonable way to describe how price and sizes are related? How could you use a line to predict the price of a house you are given if you are given its size? Well, I just kind of showed that to you, so I'm not going to do it again. But the answer is yes, that's what we use them for, as long as there is a correlation. Okay, as long as these points have some sort of pattern going on that is linear. And these do kind of follow a line. So, and that's how I answered the prior question. Okay. Number 3. Okay, so number 3 says to draw a line in the plot that you think would fit the trend in the data, which I've already done. Use that line to answer the following questions. Price of a 3,000 square foot house, which I kind of already did here. And the price of a 3,000 square foot house would be approximately $520,000. I already answered that question because I've done this before, so I knew how to do that. You might have predicted it differently, but that was probably $520,000. Whoops, that's $5 million. $520,000. I probably did that back here too. No, I didn't. Okay. B, what is the prediction of the price of a 1,500 square foot house? So I go back 2 pages and go look at this, and it said 1,500 square foot house. So now I'm going to move this green line over to 1,500, which is right here. And the size of the house is this point right here. So I would say I would approximate that at $200,000. Okay, number 5 says to consider the following general strategies students use for drawing a line. Do you think they represent a good strategy for drawing a line that fits the data? Explain why or why not, or draw a line for the scatter plot using the strategy that would indicate why it is or why it is not a good strategy. So A says Laura thought she might draw her line using the very first point farthest to the left and the very last point farthest to the right in the scatter plot. So I'm going to do just that, and I'm going to see what happens there. And I'm going to be more accurate this time. Before I was doing this line free-handed, so I'm going to choose the very first scatter plot point, and that would be right here, and the very last one is right here. And then if I get my ruler so I can draw a straight line, we'll see what happens. So I put my 0 right on that first point I chose and rotate it up like so. Then this is my best fit line right here. And as you can see, it's a fairly good fit. There's a few points up here. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8 points below. It looks like 1, 2, 3 right on, or 4, and 1, 2, 3, 4, 5 above. So maybe it's a little bit high. I might want to move it down a little bit. So that might not be the best way to do it. But that it seemed to work okay in this scenario. So Laura's is okay, I think, in this case, not always, because if the first point value is way off from the rest, then that would throw the line off. Now B says Phil wants to be sure that he has the same number of points above and below the line, and that's what I was just kind of doing, counting out to you, leading up to what Phil would do. So if Phil did that, if he wanted the same number of points above and below the line, he might take this line and move it maybe like right here, and then have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a little too many. And if I just move that back up to about here, anyhow, it's about the same. We might have to rotate it a little bit too, but we could also do that. Same number of points above and below. That could work as well, but there's going to be some values that could change that as well, and we'll lead into that. And then Sandy thought she might try to get a line that has the most points right on it. So if I do that, let's see what that would do. So now I'm going to have to rotate or something. So, or I see that there's like 4 points right here. And then if I rotate it, maybe change the slope and then move it, and then get like those 5, 6 points on that line like that. But then we have a lot of points above and none below. So that would not be a good way to do it. Okay, and if I move this up here, there's less points. And then if I really wanted to adjust this a lot, and maybe if I focused on these points here, then as you can see, if I do it like this and try to get as many points on the line this way, I might have a line something like this, where I have 1, 2, 3, 4, 5, 6, 7 points on the line, but these points are way above the line, and those are called outliers, by the way. And the more outliers we have, the less accurate our data is. So that would not be a good way to do it. And then finally, so I'll say no here. And this Phil, yeah, maybe that might be okay in this scenario, but not always. And then D says Marie decided to get her line as close to as many of the points as possible. Okay, so in other words, if Marie wants her line as close to as many points as possible, then she's going to put that there. She might rotate it up like this and then move it and not worry about how many points are above and below or how many points are on, but then get it something like that so it's really close to the majority of the points. And that is actually the best way, I think, to do this. So I would go with Marie's decision. Number 6, based on your strategies discussed in exercise 5, would you change how you draw the line through the points? So I'm going to leave that to you. There's nothing I can really say there. And number 2. Okay, example 2, deep water. Does the current in the water go faster or slower when the water is shallow? The data on the depth and velocity of the Columbia River at various locations in Washington State listed below can help you think about that answer. Depth and velocity in Columbia River, Washington State, so they have a heading. Okay, so there's a title to their table here. And it's a bivariate data. We have depth and we have velocity. Depth in feet, velocity feet per second. This source came from the Seattle Center of Education. And A says, what can you tell about the relationship between the depth and velocity by looking at the numbers in the table? Well, here's the depth in feet, less than a foot, velocity 1.55. And then here is a velocity of a depth of 11 feet, and it's only 0.22 feet per second. So looking at these bigger depths, we have a slower moving velocity feet per second. So just by looking at that, the shallower the water, or the deeper the water, let's say the deeper the water, the less velocity it has. Okay, sorry about that writing there. The less velocity it has. B says, if you were to make a scatter plot of the data, which value would you put on the horizontal axis and why? Well, I would put depth as X, and I'd put velocity as Y. And the reason is, it depends on how deep the water is, what the velocity is doing, so the depth is independent variable and the velocity is a dependent variable. Okay. Let's move on. I'm not going to write that. Number 7, a scatter plot of the Columbia River data is shown below. So the table that we had on the last page, here's what it looks like in a scatter plot. Choose a data point in the scatter plot and describe what it means in terms of the context. So I'll just pick a number. How about this one right here? And that is the point 4. This is 4, 4.5, 5, 5.5, 6. So that's halves. So that's 4.5 feet. And the velocity is 1.4, I don't know, 1.42. So what that means is when the water is 4.5 feet deep, the velocity is 1.42 feet per second. Okay, B says, based on the scatter plot, describe the relationship between the velocity and the depth. So, describing the relationship, you say, as X does something, then Y does this. So I'd say, as the depth increases, we're going left to right, as the depth increases, the velocity does what? We're up here at 1.6. It's going down as we go from left to right. So as the depth increases, the velocity decreases. How would you explain the relationship between the velocity and the depth of the water? And that's kind of the same as this here. Okay, so you may want to hypothesize why that would happen, come up with a conclusion as to why that would happen. As the depth increases, the velocity decreases. Well, why is that? You could say, well, maybe it's because the larger amounts of water moving would have to move at a slower rate because, okay, sorry for that interruption there. I don't know where I left off. So let's just say, what was I talking about? Oh yeah, the deeper the water, why is the velocity decrease? Well, the larger mass of something that has to get moved, the more you have to move, the slower it goes, or maybe other factors involved as well. Um, leave that up to you. D, if the river is 2 feet deep at a certain spot, how fast do you think the current would be? And explain your reasoning. Well, at 2 feet deep, let me just use my ruler this time. And I'm going to swing it around here so it's here. So here's 2 feet right here. Here's the 2-foot depth mark right there. And so if I were to draw a line of best fit approximating where that would be, then I would bring my ruler down here and I would draw a line like so. So there would be like my best fit line. So my approximation would be somewhere around here. So I would say probably what, 1.5? Okay, so I would say 1.5 feet per second. And explaining my reasoning, I'm not going to write it out, but there's my explanation. Okay, at 2 feet, my line of best fit intersects my 2-foot vertical line where x equals 2, and that is a y value of approximately 1.5 feet per second. Okay. Okay, and now question number 8 is just repetition, and I've already done it. It says, consider the following questions. If you draw a line to represent the trend in the plot, which I did, will it make it easier to predict the velocity of the water if you know the depth? And I would say yes, because if you do have a trend, then the trend line will intersect your depth or your horizontal line. That would be how you would determine depth of water, by knowing its velocity. So that's definitely I would say yes, it's a Y. And the reason is, if there is a line of best fit, then we can use it to predict. Now B says, draw a line that you think does a reasonable job to model the trend of the scatter plot in exercise 7 and use that line to predict the velocity when the water is 8 feet deep. Well, I've already drawn the line, so let me just get rid of this line here. And 8 feet deep, I've just got to move this line over here to 8 and see where it crosses. And then if I take my ruler and make it horizontal, and I look, and it's right here. So it's just under 0.8. So I would say my approximation would be 0.79 feet per second if the water is 8 feet deep. Okay, now it says use the line to predict the velocity for a depth of 8.6 feet. How far off was your prediction from the actual observed velocity for the location that had a depth of 8.6 feet? So now we're going to use the line to predict the velocity of a depth of 8.6. So I go back here, and a depth of 8.6, if I move this over, here's 9, here's 8.5, so 8.6 is approximately there. And if I bring my ruler over here, then now I am up here, or down here I should say, at 0.6, I don't know, 68. Let's say that's about 0.68. So I'd say 0.68 feet per second. So this said to draw a line where you think the model would be at 8 feet, and then it said 8.6, find the velocity at 8.6 feet. Okay, so you can see that from depth of 8 feet, adding 0.6 feet, then it did decrease in speed or velocity. Okay, that is the end of lesson 8. Review the lesson summary and go do your problem set.